Well, we continue the proceed to our seminar part, and I ask you to remind the tasks for today. If I remember, there was a task about the symplectic leaves. Symplectic leaves in SL2. Maybe something else. Is this statement is well understood? So if H and F are functions on our Poisson manifold, and X, H is the vector field corresponding to the function H, so it is dH over dxj Pij d over dxi. Then there is a yes, I remember I have demonstrated it. So X of H F is equal to the commutator of Hamiltonian vector fields corresponding to such functions. Okay, I remember. I'm sure that they were a task to describe symplectic plectic leaves on SL2 on the dual space to the SL2R. So if this is M, then we consider some subring in the space of smooth function on this space, which is just the polynomial algebra R of SL2. So it is our principal example of Poisson algebras, the symmetric algebras with generators from the Lie algebra. Let us discuss this problem. It will be important in many contexts. Are there some ideas in the online audience to describe symplectic leaves on our principal example of Poisson varieties? S. Symmetric tensor algebra of the algebra SL2. Jean-Long Chen, have you done this homework?
Sorry, I don't know how to solve this. I have tried, but don't know how to solve it.
But could you describe what to do? So what is the symplectic leaf in this situation? Do you remember the definition?
Well, yes. Symplectic leaf is a level set which for any x on this manifold,
Yes.
Cix equals to Ci for any the Ci is the Casimir function.
Very good. What are the Casimir functions on this Poisson manifold?
I think it's the trace setting E11 plus E22.
Okay, the trace, but on SL2 it is 0. You remember? So you will be right if I replace here the Lie algebra by GL2. It's okay. We can work with this definition, but there is another another central function which is the determinant. Do you remember?
Yes.
Uh-huh.
E11, E22 minus E12,
Yeah.
and E21.
So principally, yes, and these functions generate the center. Do you? Yeah, we have commented this. So we have associated this idea with the problem of invariant functions on matrices with respect to the adjoint action of the group. So we described that we have understood that the center is two-dimensional. There are no other functions. So how to describe the asymplectic leaf? We know now the central functions, the Casimir functions. What is the symplectic leaf? John Longchen, please say what do you think?
So I think because these determinants are the center, are the Poisson center, then we must find some combinations E11, E12, etc. And we try to get this CIX equal to CI, and then we can get the symplectic leaves. Okay,
but how to describe these leaves geometrically, algebraically? Do you remember? We have commented this.
Sorry, I forgot.
So we can see the matrices M, or it's better to use another letter A. Just with these coefficients. So we consider E as functions on matrices, the coordinates on matrices. The matrix element here are coordinates on the space of matrices. And consider C trace as constant 1, and the determinant of this matrix A is constant 2. These conditions define a matrix with fixed eigenvalues. You understand?
Yeah.
For generic C1 and C2, MC is the space of matrices A such that with fixed eigenvalues. You understand how the eigenvalues are related with numbers C1 and C2. The roots of lambda square minus C1 lambda plus C2. Okay?
Okay, yeah.
Because we interpret C1 as a trace of a matrix and C2 as a determinant of the matrix. So if we, for generic C1 and C2, the roots of this characteristic polynomial are different, and it means that the matrix is diagonalizable. So the matrix A is something like G lambda 1, G2, lambda 2, G minus 1. So this matrix can be put into the diagonal form. And this element G, it can be chosen by non-unique way. G can be chosen in a non-unique unique way. G multiplied by some d1, G d1 0 1 d2 gives the same representation, provides the same representation. Junlong Chen, please say if the logic in this calculation is clear, or I should comment it in more details.
The G corresponds to G times that D1 and D2 is not very clear for me. The last one.
Okay.
The last one.
Okay. So our task is to describe symplectic leaves, to introduce some good coordinates on the symplectic leaves. You see, we should understand how the symplectic form is organized on this submanifold. So we have to introduce some good coordinates on these symplectic leaves, on these subvarieties. We know that the subvariety is a set of matrices with fixed eigenvalues. Okay? This formula, I'd like to use this formula to parameterize the matrices with the same eigenvalues. And the statement here is that G, so you know that each diagonalizable matrix can be represented in this form. Each diagonalizable matrix with fixed eigenvalues lambda 1 and lambda 2 can be represented in this form. But the choice of matrix G is not unique. If we just change G by G multiplied by a diagonal matrix on the right, it will give the same formula. So if we denote this by G prime, then this is equal G prime lambda 1, lambda 2, G prime minus 1. It is just equal because this diagonal matrix commute with lambdas. It is equal G d1 d2 lambda 1 lambda 2 d1 minus 1 d2 minus 1 G minus 1. I have written what is here given by G prime. But you see the diagonal matrices commute between them. So we can transport this diagonal matrix here, and then they cancel each other. So it is just equal by G lambda 1, 0, 0, lambda 2, G minus 1. So my statement is that if you found such a representation, a matrix G multiplied by generic diagonal matrix on the right gives the same representation for the matrix A. So to choose coordinates, we have to specialize the matrix G, matrix element of the matrix G. And I propose to do the following. Let's specialize G in the representation in 1 of the form G is equal, how to specialize. For example, I can choose the diagonal elements to be 1. Means by this freedom of multiplication of a diagonal matrix on the right, I can choose some particular elements on diagonal. Okay?
Yes, it's clear now. Thank you.
So you see now you get two variables. And I pretend to say that they are good coordinates on our symplectic leaf, which is two-dimensional. Is it better now? Uh-huh. Now we should calculate this formula. So I propose coordinate x and y as a coordinate on a symplectic leaf. Please do it now. And next we should calculate the Poisson brackets in terms of x and y. Zhanglong Chen, do you understand what to do now?
Well, yes, we have that G equals to 1x and y1. Then our aim is to find A. Then we just use that.
Yes.
A equals to that.
Yes. Very good.
We should define that A.
And then we have to calculate the Poisson bracket on the symplectic leaf in terms of the variables x and y. Okay? Just to demonstrate that it is not degenerate. So that we have a symplectic manifold. Our leaf, our level set of central functions is a symplectic manifold. Zhanglong Chen, could you do it on the blackboard in Zoom?
I don't know how to do it on the blackboard. I don't know how to try it. Sorry.
But do you have a stylus? Do you have a stylus?
Stylus? What?
If you have stylus, you can now make comments. So first of all, we have to calculate G minus 1, and then a parameterization of matrices A in our level set in terms of variables x and y. Very good. I can see.
1x, y, 1, and A equals to G lambda 1, lambda 2, G minus 1. Equals to this x
It's quite reasonable. Yes. So now you have parameterization of initial variables. You see the variables Eij in terms of central functions, Casimir functions, lambda 1 and lambda 2. They commute with all functions. And some functions x and y. So now you have different parameterization of the same space of matrices. In place of Eij, you have coordinates lambda 1, lambda 2, and x and y. Okay?
Not quite clear, sorry.
It's the same matrix A as the initial matrix A. You see?
Yes.
With coordinates Eij.
Yes, which is equal to, let's say, E11,
Yeah.
E1, E22,
Exactly.
E12, and E21.
Okay. You know the Poisson brackets between Eij. Now you have to
Yes.
calculate the Poisson bracket between x and y. What is the Poisson bracket on the coordinate x and y?
So it should be, let's say, lambda 1 minus xy, lambda 2, lambda 1, not 2, is the Poisson brackets of E11 is 0. No.
You see, it is E11. You have just the identification.
Oh, yeah, it is E11.
So my proposition is the following, that let us calculate the Poisson bracket of E11 with E12, but in terms of x and y.
Oh, yes,
And
I see, so it should be
this will
x.
give you the Poisson bracket between x and y.
Oh, yes, now I see, yes. Okay, so let's say lambda 1 minus xy, xy lambda 2, and x lambda 1 plus x lambda 2. This Poisson bracket equals to, this is E11, E12.
Yes, and what is this Poisson bracket?
Okay,
But what is this Poisson bracket initially on GL2? It is E12.
Yes, it is, because this K and J, J and K is equal, then this should be E12.
E12. And we now have to express E12 in terms of x and y else.
Yes.
And you forget the denominator. It is important.
Oh, yes. So this is minus E minus xy. So E12.
And inside the Poisson bracket. Yes, because it is the Poisson bracket of matrix elements. So you have to plug this denominator into the Poisson bracket. Yeah, very good. Yeah.
Now we calculate this Poisson bracket.
Yes, and it should be the same as E12, which is also given by this matrix element.
Yes.
And now we have to apply the fact that lambda 1 and lambda 2 are central. So their Poisson bracket with all things are trivial. And there is the only non-trivial Poisson bracket of x and y. So, and by this knowledge you can extract the Poisson brackets of x and y. Is it clear now?
So lambda 1, the Poisson bracket of lambda 1 is 0. So now the only non-trivial one is we have the one with lambda 1 and another with lambda 2.
Lambda 1 and lambda 2 they are functionally expressed in terms of C1 and C2. So it's a different basis of function of Casimir functions. You know that C1 is lambda 1 plus lambda 2, and C2 is lambda 1 multiplied by lambda 2. So if C1 and C2 are Casimir functions, lambda 1 and lambda 2 are Casimir functions too. So
Yes.
lambda 1 and lambda 2 Poisson commute with all functions. The only non-trivial Poisson bracket is between x and y.
Okay, yes, I see.
And our goal to demonstrate that it is not zero. So that
Yes.
we got a symplectic variety. Our level set is a symplectic variety.
I see.
Is it evident that it is not zero?
Is it because we have this denominator?
No, because it is equal E12. It is something non-trivial. Yeah.
This one is equals E12.
E12.
So it is not zero.
It is not zero because if not, if it would be zero, this Poisson bracket will be zero.
Yeah, but this Poisson bracket is equals to E12,
Yeah.
so this is
Yes.
zero.
But however, could we express this Poisson bracket in terms of the Poisson bracket of x and y?
X, y squared. It's not. Sorry, Professor, but how do we calculate this Poisson bracket?
Just by the Leibniz rule. Yep.
Okay, so we use the Leibniz rule for these two Poisson bracket as well.
Yes. We need so. But you see, in the first Poisson bracket, you have to take only the Poisson bracket with the first multiplier, because with the second it will be zero.
So that should be minus x lambda. This should be Poisson bracket.
I have corrected rapidly. You see, I transmitted the right Poisson bracket one position left.
Yes. Yeah. This is the one. Yes.
Uh-huh.
Similarly for this.
No.
This we will have two terms.
No,
This one
here you will have two terms. Yeah.
Okay, so equals for this one equals to minus xy equals to lambda 1 minus xy lambda 2 1 minus xy.
Do you see that the last term is trivial?
Because we have both lambda 1 and lambda 2.
Because we have both functions depending on the same product of the same product of x, y.
Sorry?
Both functions are functions on the product of x, y. It means that they are functions on some one variable. And two functions on one variable always Poisson commute. Is it clear? This term is trivial. So my statement is the following, that xy with xy is 0 for every Poisson bracket. Okay? And it means that if you calculate some function x of xy with some function g of xy, it is also 0 because it is f prime g prime xy xy. Okay? So my statement is the following. Xy with xy is 0.
Yes. Xy with xy is 0, yes.
It is obvious. And f of xy with g of xy is also 0. For each functions f and g. Do you agree?
Why it is true?
Because then you calculate such an expression, you apply the differentiation of complex functions. So it is equal to f prime g prime of xy xy.
Oh, okay, yeah. So this functional depends on xy. And
yes, and they're different, but they depends on one variable. It means that when calculating this Poisson bracket, we will descend to the Poisson bracket of the same variables, which is 0. It doesn't depend on which variable we consider. So the last term is trivial. Let us.
Yeah, time is 0.
Yeah.
So we calculate this one. This one. So this Poisson bracket x and y.
Yeah.
X, y. This depends on xy, but this depends on x. So okay. So
it could be non-trivial.
Yes. So minus xy x lambda 1. So it's minus 1 lambda 1 x y x. Is it correct?
Yes, yes, I suppose, yeah.
Okay.
Minus 1 because it is, okay, yeah. I'm sorry. I suppose that one other minus 1 should be. Because in the denominator you have minus xy.
Yes. So
One minus is from the fact that it is in the denominator, and another minus 1 in front of xy.
Oh yes.
So it should be plus.
Yeah. Should be plus. Yes.
Should be plus. Yes, and xy with x. How to simplify this?
So we use the Leibniz rule.
Yeah.
Minus x y squared.
Perfect.
X
xyx plus 1 bracket of yx. Yep.
0.
No, it's not there.
Plus y x. So it is 0.
Yeah.
So
yes.
we only have this lambda. Lambda 1x.
Yeah.
1 minus x y squared minus xy.
Very good. The second term is similar with lambda 2.
1 minus xy. So we have minus lambda 1 plus lambda 2 x 1 minus x 1 squared x y. Okay, so that's it. For the second term, we have minus lambda 2 times minus lambda 1 plus lambda 2 of x, y, x.
Very good. You understand the principles. Yeah.
So this equals to this minus lambda 2 minus lambda 1 plus lambda 2 x if we change this to plus, let me see, this is xy. So this is plus 1 minus xy squared times lambda 2 minus lambda 1 plus lambda 2 x y.
Yeah.
So we combine these two coefficients together, and we get an expression for just x and y.
Yeah.
Also brackets.
Yeah.
Okay.
And you know the answer. Maybe it's better to write the answer to subtract some factors. I suppose that the square of 1 minus x y will disappear.
So we have this the cube of
Uh-huh.
1 minus xy here, but we have just square of 1 minus xy here.
Mm-hmm.
Okay, so lambda 1 minus xy. 1 plus 2 x
Будь здоров.
plus lambda 2 lambda 1 plus lambda 2 1 minus x y squared x y.
You forgot x.
Oh yes, yes. So x, yeah, x. Okay, so we combine this. Let's say lambda 1 squared plus lambda 1 lambda 2 minus xy lambda 1 minus xy lambda 2 plus lambda 2 squared minus lambda 1 lambda 2 x. No. Sorry, not. Two squared times 1 minus x y. You.
Mm. No. Yeah. Multiplied by x plus.
X, yes.
Yeah.
Yes.
Uh-huh.
X lambda 1 squared plus x lambda 1 lambda 2 minus x squared y lambda 1 minus x squared y lambda 2 plus x lambda 2 squared minus x squared y lambda 2 squared minus x lambda 1 lambda 2 plus x squared y lambda 1 lambda 2.
Okay.
So over 1 minus x y cube. So this cancels out, and x, and so what's x lambda plus x lambda 2 squared. So that's this, that's the this 2 minus x squared y lambda 1 minus x squared y lambda 2 minus x squared y lambda 2 squared plus x 2 y lambda 1 lambda 2.
Okay. It's a little bit strange, but I don't see simplification. So I suppose there are some mistakes, but the principal thing to understand that it is not trivial. It is a not trivial Poisson bracket on xy.
Yes.
Okay, thank you very much. It's the style. It's the style of exercises of tasks I wanted to understand. So, okay, we stop here for these tasks, and in the rest 15 minutes we will discuss the task about the Kepler problem. So please see the formulation. So we will understand why it is integrable in the Liouville-Arnold sense. So how to construct the involutive independent family of integrals. But let's start to reading the tasks and to discuss what is unclear in formulation. Gianluigi Paganini, could you be the next speaker?
Yeah, of course. But I can see the blackboard.
So firstly, could you repeat the task? How you understand the task?
Of the Kepler problem.
Yeah, of the integrable, of the Liouville integrability of the Kepler problem. How you understand this task? What to do?
So to find the family of evolutive integrals, motion.
Yes. So I have demonstrated that there is a family of integrals of motion, just the angular moment, just the Hamiltonian and 3 angular momentum. But I claim that they are not involutive. Do I understand that they are not involutive? Could you write down the Poisson bracket between components of the angular momentum?
So first, I think it's better to start with the commutation of the angular momentums.
Very good.
So in this case, we have in general J I J, and as we have seen, the commutator between the angular momentum is given by this case we can write the epsilon symbol. In this way.
Yeah, very good.
So they are not involutive, even though they commute with the Hamiltonian. So in this case, we don't have for the angular momentum such a family of integrals. And now.
But what do you need now for the Liouville integrability? How much involutive integrals we have to find?
In this case, just three.
Just three, yeah. Because we have a 6-dimensional symplectic manifold. 6-dimensional. What do you think? Do you have some ideas how to find three involutive integrals?
And try to exploit the conditions on the three independent integrals. So to try to find some objects which must satisfy first of all the commutation with the Hamiltonian.
Yeah.
So here we need to have 0, and also for these objects we need to have the same relation. So I would say we can try to impose this kind of condition on from these objects, and try to find we can say a combination which allows us to find the analytic form of the eyes.
Okay. I propose to combine the involutive integrals with the help of angular momentum. So in the polynomial algebra of angular momentum, we have to find two involutive integrals.
Maybe we can try to find the combination with...
Some combinations, yes, but not linear, in fact.
Okay. So we can try to write something like AI.
So you see, all functions on J commute with H.
Yes.
Because all J commute with H. All functions on J commute with H.
Yes.
So I propose to find in a ring of functions on J two commuting functions.
Yeah, I would say we can try, for example, to add the angular momentum. Also, I would say in this case the coordinate, for example.
Yes.
Because they commute with the Hamiltonian.
The angular momentum.
Yes, I would say I can write something like this, and we add another term in order to find the I here. So in this case, since for the Kepler problem we have, for example, both momentum and position.
Yeah.
We can try to, for example, add with some coefficients we can say, for example, C Q and Q plus CP and in this way. And after we can try to impose this form, or better the conditions in order to find the coefficients for.
Gianluigi, do you remember the idea of homogeneity when we studied the center of our Poisson algebra, of Poisson-Lie algebra of GLN, GL2? We looked for Casimir element only in homogeneous components. That is due to the homogeneity of the Poisson bracket. So if you find some expression which is not homogeneous, all its homogeneous parts should be central. When you look for Hamiltonians, in our case, it gives the very similar idea. So it is more convenient to start looking at the homogeneous expression. So I don't quite understand your expression of linear combinations with just coordinates.
I mean, since my reason was that since we are looking for some objects that commute with the Hamiltonian, that commute with each other, and since we already know that we can use, for example, the angular momentum, we can try to have the other terms and see, for example, if we can construct, for example, from the angular momentum, adding these new terms, some new object. This was my reasoning.
Yes. Okay. You can try.
So, for example, since we can try to, for example, to use the first condition. So in this case, we can write the Hamiltonian, and we already know that with Ji there is a commutation. So in this case, we also have here a Ji plus so now we can try to evaluate this.
Yes, you can.
And for example, for Ji, we already know that it is equal to 0.
Yeah.
After we have the expression for the Hamiltonian, which contains just the Q and the P. So in this case, we have, for example, we can explicitly write the Hamiltonian, which is 1/2.
Do you remember the Poisson bracket of H with Q?
Yeah, it was.
It is P.
Yeah, it is P. It is P. So wait. Okay. Okay. So for the first term we have a CQ, which is just a constant. We can use the bilinearity. And so H QI, which is just PI, plus the other term in which we have instead plus CP and the Poisson bracket. between age and pi, which is minus alpha qi
Yeah.
over q. Okay.
Very good. You see that there is no chances to be zero.
Yeah, we need to impose the
Yes, we need some
Yeah.
additional idea. So maybe it will stay your home task, but I'd like to stress your attention on the fact of coincidence of Lie algebra of angular momentum and the Lie algebra SO3. Do you remember?
Yeah, of course.
Uh-huh.
They have the same relation. So, I mean, the Poisson bracket between the angular momentum in this case is satisfies the same the algebra relation for SO3.
Okay, I switch off the whiteboard. I just give you some comments and we will stop for today. So you are absolutely right that the Poisson bracket is the complete antisymmetric tensor epsilon. And the next thing that this algebra is equivalent to SO3, which is the linear space of skew-symmetric matrices n by 3 by 3, such that A is minus A. Such matrices could be parameterized by 3 variables x, y, and z. And my statement is that it is equivalent. So if I introduce a basis E1, which is a matrix E2 and E3, then this parameterization of x, E1, E2, I'm sorry, minus, here minus, and here plus z, E3. This is the identification, this is an identification of this identifies SO3 with R3 with just the vector product. You see, R3 with the vector product is a Lie algebra. And SO3 is also a Lie algebra with respect to the commutator of matrices. So my statement is that this formula make this identification, and it is the same Lie algebra as the Lie algebra on angular momentum. This is an indication to solve our problem of complete integrability of the Kepler problem. And it will stay the task for the next time. We finish for today. Good continuation, and see you next week.